In this video, we will quantify and analyze solution variables for a counterflow plate heat exchanger. We will review the calculated residuals, ensure mass and energy conservation, and create contour and vector plots on an interior plane. If you're continuing directly from the solver, you should see the residuals in the display. Otherwise, to load in the data independently, go to File, Read, Case and Data. To plot the residuals, go to Results, Residuals, and Plot. We can see that the continuity and momentum equations are well below their convergence criteria of 10 to the negative third. During the setup, we changed the energy criteria to 10 to the negative ninth. And we can see here that energy has also hit its goal, which caused the solution to terminate well before our 1000 iteration mark. Just because we reached our convergence criteria does not ensure that the flow properties are unchanging or that mass and energy are conserved. Let's check our report plot of the oil outlet temperature. This shows us the solution convergence on the outlet faces. Here, we can see the initial value and it reaching its steady state solution. Next, let's verify that mass and energy have been conserved. On the ribbon, click Results and Fluxes. We'll choose all the oil inlets and outlets as well as the water inlets and outlets. We can see our inlet boundary conditions as expected. The net mass flow is many orders of magnitude lower than any of the inlets or outlets in the domain, which tells us that mass was conserved. Let's check the total heat transfer rate. Again, we can see that the net results are orders of magnitude less than any of the inlets or outlets. Let's quantify the average outlet temperatures. Under Reports, choose Surface Integrals. Change to Mass Weighted Average. Choose Temperature from the Field Variable list. And choose the oil outlets. For the oil, we see approximately 341 Kelvin. We can see a higher temperature at outlet 4. This is the plate that has water only on one side, so it makes sense that it is at a higher temperature. We can calculate the water outlets as well. Here we see about 310. Next, let's create an interior plane so we can view the velocity and temperature inside the domain. First, we'll display the mesh so we can be certain of where to place the plane. Choose Mesh and New. Deselect all the surfaces. We'll choose all of the intermediate walls, as well as all the side walls. We can include the top and the bottom as well. If we expand graphics in the outline view, we can see our mesh object that we just created. We'll want our plane to be in the YZ plane, with a normal vector in the X direction. Go to Create and Plane. We'll call it Plane X Mid, and we'll use Point and Normal as the options. The midpoint in the X direction is half the plate width. Type 0.58 meters for the X0 point, and leave 1 in the IX for the normal vector. Double-click Mesh 1, the one we created earlier, and add the plane to the display. Now that we have our plane in the correct location, we can add contours to it. Click Contours and New. We'll do temperature first. We'll do it on the plane we just created. We can disable the lighting in the View tab to get a better image. Here we can see the hot oil coming from the right and the cold water coming from the left. We can switch to velocity contours. Here we can see the constant inlet velocity develop into a more parabolic velocity profile downstream. Since we have a counterflow heat exchanger, it may be more interesting to plot velocity vectors instead of contours. We'll go to Vectors and New, and again we'll do it on our plane. This is difficult to see, so let's change the scale to 0.3 and the style to filled arrow. Now we can easily see the parabolic velocity profiles that developed over the domain due to the default no-slip wall boundary conditions. If we zoom in close enough to one of the domain interfaces, we can see the vector directions change in association with each fluid. This concludes our demonstration. Thank you for joining us.